Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine standing in front of a mirror. Just, looking at your normal reflection.
Right, just checking your hair or whatever.
Yeah, exactly, adjusting your collar. But suddenly, the glass shifts. And instead of just showing your face, the reflection starts playing backwards.
Like a movie on rewind.
Yes. And not just by a few hours or like a few days.
Yeah.
Imagine the reflection rewinds faster and faster, dissolving the room right behind you.
Just completely falling away.
Right. The walls fall away. The city outside dissolves into this wilderness. And the Earth itself literally unforms. It turns back into a swirling disk of dust. The sun breaks apart.
You're going back to the very beginning.
All the way back. The mirror pulls back, accelerating through deep time. Billions of years just collapsing in seconds, retreating to a time of absolute, just unimaginable density. Everything you've ever known shrinks into a blinding, searing point of heat. And then the mirror just pauses.
It hits play.
Hits play. You are suddenly watching the entire 13.8 billion year history of the cosmos play out in fast forward right there in the glass.
Which, it sounds like pure, unadulterated science fiction.
Totally.
But the crazy thing is, humanity's essentially building that exact mirror right now.
It's wild to even think about. We are currently undertaking one of the most ambitious computational projects ever attempted in the history of our species.
Oh, without a doubt.
Recreating the formation of the universe itself from its very first breath inside supercomputers.
The sheer audacity of the project is what makes it so compelling, honestly. Because when we talk about these computational reconstructions, we really have to strip away the idea that these are just high-definition animations.
No, it's not a Pixar movie.
Exactly. We aren't painting pretty pictures of stars and galaxies on a digital canvas just so someone can use them as a desktop wallpaper.
Though they do make great wallpapers.
They do. But we are constructing immense, dynamic, physical laboratories in silicon. These are mathematical reconstructions built rigorously, line of code by line of code, from the ground up.
Driven by the actual math.
Yes, they are governed by the precise, unrelenting equations of gravity, thermodynamics, radiation transfer, fluid motion, all of it. Cosmic expansion.
So, by taking the absolute limits of observational astronomy and fusing them with the bleeding edge of supercomputing architecture, we're attempting to mathematically weave reality together, just to see if we truly understand how it works.
Exactly.
So today, we are going to explore exactly how scientists are building these dynamic reconstructions of reality. You, listening to this right now, are about to see how the invisible forces that shape literally everything around us are being mapped and tested and ultimately understood.
It's a huge undertaking.
It really is. We're going to dive into the actual mechanics of how you take the raw, chaotic math of the cosmos and turn it into a breathing, evolving universe inside a machine. Because, honestly, there's a profound philosophical weight to this.
There is. It forces a real reckoning with our own place in the grand scheme of things. Think about it. We are a temporary biological species residing on a tiny rock.
A very tiny rock.
Attempting to mathematically model our own origins. We are building virtual universes to understand the singular physical universe that gave birth to us.
Which is just wow.
It forces us to confront the deepest questions about the nature of reality. And how unbelievable complexity like galaxies, stars, planets, biology, consciousness itself, how all of that emerges from incredibly simple initial conditions.
But let's look at the immense roadblock right at the starting line. Because the fundamental challenge of understanding the cosmos, and therefore, the very first challenge of simulating it, is deeply frustrating.
It's a massive headache.
It's the fact that the vast, overwhelming majority of the universe is completely, utterly invisible to us.
Right.
The stuff we know, ordinary matter, the atoms that make up the stars, the planets, the glowing gas clouds, the device you're listening to this on, and our own biological bodies that constitutes just a tiny, almost negligible fraction of cosmic reality.
Around 5%.
5%. That is nothing.
It really isn't. Which means if you want to build a universe in a computer, you absolutely cannot start with ordinary matter.
Because it just wouldn't work.
Right. If you build a universe using only atoms, your simulation will fail catastrophically. It won't look anything like the night sky. The universe is completely dominated by two deeply mysterious, totally invisible components: dark matter and dark energy.
The big two.
The big two. Dark matter acts as the vital gravitational scaffolding. It is the structural foundation that actually allows galaxies and massive galaxy clusters to form in the first place.
And then dark energy.
Dark energy is the enigmatic force driving the accelerating expansion of space itself.
And we can't see either of them.
No, we cannot hold either of these in a jar. We don't even have a standardized particle model for dark matter yet, but their silent, invisible influence dictates absolutely everything, both the structure and the ultimate destiny of the cosmos.
So I want to focus on the mechanics of getting this started. If you are a computational astrophysicist sitting at a supercomputer terminal and you want to simulate this invisible universe, where do you even begin?
You definitely don't just write a command prompt that says run universe.exe and walk away.
I wish it was that easy.
Me too. But no, you have to give the computer a highly specific starting state. You need initial conditions.
Okay.
And those initial conditions are drawn from something called the cosmic microwave background, or the CMB.
Right. So the CMB is what, like the baby picture of the universe?
Basically.
Yeah.
It is the Rosetta Stone of cosmology. Massive cosmological simulations must begin with the conditions inferred from that early universe. The cosmic microwave background is the ancient relic radiation left over from the Big Bang.
So it's light.
Yes.
Yes.
Specifically, it is the light emitted roughly 380,000 years after the Big Bang, during an event called recombination.
The recombination, what's happening there?
That's when the universe finally cooled down enough for the first stable atoms to form, which meant light could finally travel freely through space without just smashing into a dense soup of particles.
Ah, so it cleared up.
Exactly. It's the oldest light we can possibly see. And preserved within that ancient light, kind of like insects trapped in amber, are tiny, almost imperceptible density fluctuations from when the universe was extremely young.
Let's talk about the scale of those fluctuations, because it's really hard to wrap your head around. When we say tiny, we really mean minuscule.
That's absolutely tiny.
The differences in density across that early universe were smaller than 1 part in 100,000.
Yeah, just barely there.
Imagine a perfectly smooth, vast ocean, and the only waves on it are microscopic ripples.
Great analogy.
Yet those incredibly faint quantum fluctuations, which were blown up to macroscopic size during an early period of rapid inflation, those were the seeds of absolutely everything that exists today.
Every galaxy, every star, you and me.
We all trace our physical lineage back to those microscopic density irregularities.
And the physics of why those specific tiny seeds grew is the entire foundation of the simulation. Gravity is the ultimate patient sculptor here.
How so?
Well, under the influence of gravity, those slightly denser regions of that primordial soup, the regions that were just a fraction of a percent denser than the average, they exerted a slightly stronger gravitational pull than the less dense regions around them.
Because more mass equals more gravity.
Exactly. So what happens? They gradually attract more matter. It is a compounding runaway effect. Over hundreds of millions and then billions of years, those 1 in 100,000 irregularities undergo what we call nonlinear gravitational collapse.
Nonlinear gravitational collapse.
Right. They draw in more and more dark matter, pulling it out of the surrounding voids and weaving it into these enormous, dense structures.
I always think of the CMB as this blurry, static ultrasound of the infant universe. It gives us that initial snapshot. And the dark matter acts like an invisible, ghostly skeleton growing out of that snapshot.
I like that. The skeleton holding it all together.
Yeah. We can't see the bones directly, but we know exactly how they are shaping the glowing flesh of the galaxies resting on top of them. We know the skeleton is there because we see the exact shape of the body it supports.
And historically, this was a massive revelation. Back in the 1970s and 80s, when cosmologists first started running these primitive N-body simulations.
Wait, what's an N-body simulation?
They're computer algorithms that calculate the gravitational forces between thousands or millions of individual particles. So when they started running these, they realized that without dark matter, there simply hadn't been enough time since the Big Bang for ordinary matter to clump together and form the galaxies we see.
It was too slow.
Way too slow. Ordinary matter is coupled to radiation in the early universe, so it just gets pushed around. It couldn't start collapsing until that 380,000 year mark.
But dark matter could.
Yes. Dark matter doesn't care about light. It is collisionless. It started collapsing much earlier, creating these really deep gravitational wells. So by the time ordinary matter was free to collapse, the dark matter foundations were already laid out, just waiting for the gas to fall in.
Wait, I want to pause there. Because you just mentioned that dark matter is collisionless.
I did, yes.
What does that actually mean in the context of coding a simulation? How do you code a collisionless fluid?
It is a brilliant mathematical abstraction, honestly. In a computer, we don't simulate individual dark matter particles, because if dark matter is composed of subatomic particles, there would be an impossibly large number of them in even a cubic millimeter of space.
Right, the computer would just explode.
Instantly. So instead, we use macroparticles. A single particle in the simulation might actually represent the mass of 1 million suns worth of dark matter.
Oh, yeah, okay.
And because it is collisionless, it means these particles don't experience friction or pressure when they pass through each other.
They just phase through.
Exactly. If two clouds of ordinary gas collide, they heat up, they slow down, they emit X-rays. If two clouds of dark matter collide, they literally pass right through each other like ghosts, interacting only via their mutual gravitational pull.
That's incredibly eerie.
It is. So the code simply has to solve Poisson's equation for gravity. It calculates the gravitational force every particle exerts on every other particle, moves them a tiny step forward in time, and then recalculates.
But calculating the gravity of every particle pulling on every other particle, if you have billions of particles, doesn't the math get exponentially out of control?
Yes. Highly out of control.
I mean, I remember from high school physics, the gravitational force between two objects is easy. But if you have 10 billion objects, calculating the distance and pull between every single combination of two objects sounds like it would melt a computer.
You've hit on the exact computational bottleneck that plagued all those early simulations. If you use a naive brute force calculation, what we call an ON squared algorithm, the time it takes to compute grows with the square of the number of particles.
So for billions of particles...
For billions of particles, the universe would end before the simulation finished.
That's a problem.
A huge one. So computational astrophysicists had to invent these brilliant shortcuts. And one of the most famous is the tree algorithm, which was originally adapted from methods in plasma physics.
How does that work?
Well, imagine you are looking at a forest from, say, 10 miles away. Do you need to calculate the gravitational pull of every individual leaf on you?
No, obviously not.
Right. You group the entire forest into one massive object and calculate the pull from its center of mass. The tree algorithm divides the simulated universe into a hierarchical grid.
Okay.
If a group of dark matter particles is far enough away from the particle you are currently calculating, the computer just treats that distant group as a single combined mass.
Oh, that's smart.
It drastically reduces the number of calculations required, changing the computing time from ON squared to ON log n. And later, they combine this with mesh grids, where you calculate the gravitational field on a 3D grid and interpolate the forces resulting in tree-PM, or tree-particle mesh algorithms.
Tree-particle mesh, got it.
That breakthrough is exactly what allowed us to scale up from simulating a few thousand particles in the 80s to literally trillions of particles today.
That's incredibly elegant. We're using computational geometry to sort of cheat the math just enough to make it run without losing the macro accuracy.
Precisely.
Okay, so we have this optimized collisionless ghost skeleton of dark matter forming in the computer. But if we run this simulation, what does it actually look like? Because it's not just a random scattering of spherical blobs, right? It has a very specific, almost biological architecture.
It does, and it is arguably one of the most stunning discoveries verified by these simulations. The dark matter organizes into what we call the cosmic web.
The cosmic web.
Imagine vast, interconnected filaments of dense matter stretching across unimaginable distances of space. Where these filaments intersect, you get these massive, hyperdense knots called halos.
Halos, okay.
And between these luminous threads lie enormous, terrifying voids. Regions of space millions of light years across that contain almost nothing at all.
Just dead space.
Exactly. And this web-like structure wasn't programmed into the computers directly. It arises naturally, inevitably, just from the gravitational evolution of those tiny CMB fluctuations.
I want to make sure I'm visualizing this correctly. It's like watching water trickle down a bumpy windshield. It naturally pools into streams and droplets, leaving empty spaces between.
That's a really good way to picture it. The process is often described by the Zeldovich approximation. Initially, matter collapses along one axis, forming vast, flattened structures we call pancakes.
Pancakes. Cosmologists are great at naming things.
They really are. Then it collapses along a second axis, forming the long, stringy filaments. Finally, matter flows along those filaments and collapses along the third axis into the dense nodes, those dark matter halos.
And the voids.
The voids are just the regions that lost the gravitational tug of war. They slowly empty out as all their material is pulled toward the filaments.
So in our supercomputer, we now have this beautiful twisting skeleton of dark matter. We have these dense halos acting as massive gravitational sinks. But we are missing the stars.
We are missing the light.
Right. We are missing the galaxies. We need to introduce ordinary baryonic matter, the
Right.
gas. But wait, if gravity alone creates this beautiful dark matter web, why can't we just stop there? What goes wrong in this simulation if we hit play with only gravity and no ordinary gas?
Well, if you only simulate gravity, you get a highly accurate map of where galaxies should be, but you don't actually get galaxies. You just get cold, dark gravitational wells.
Empty bowls.
Exactly. To understand the actual universe, you have to throw gas into those wells. You have to introduce hydrodynamics. And this is where the simulation goes from being a relatively clean, elegant mathematical exercise into an absolute nightmare of complexity.
I find this historically fascinating. It's so counterintuitive that the stuff we understand best, ordinary matter, the gas, the stuff you and I are made of, is actually the hardest thing to mathematically simulate.
Oh, without a doubt.
Meanwhile, the dark matter that we fundamentally don't understand at a quantum level is computationally much simpler because it's a one-trick pony. It just does gravity. But ordinary gas is a diva.
A diva is putting it mildly. Gas dynamics involve massive chaotic turbulence. When ordinary gas falls into a dark matter halo, it accelerates. And as it accelerates, it heats up to millions of degrees, creating supersonic shock waves that just ripple out through the space.
That sounds intense.
It is. You have incredibly complex magnetic fields twisting, snapping, and reconnecting. You have to calculate the cooling functions because gas can't form stars unless it cools down, and it cools by emitting radiation, which requires tracking the specific atomic transitions of elements like hydrogen, helium, and oxygen.
That sounds computationally punishing. You can't just use those dark matter macro particles for gas, can you?
You can, but you have to modify them entirely. There are two main approaches to handling the gas. One is grid-based, where you divide the universe into millions of tiny cubic cells and calculate the flow of gas between the cells using the Euler equations of fluid dynamics.
Then the other.
The other is particle-based. It's called smooth particle hydrodynamics, or SPH. In SPH, the gas is represented by particles that carry properties like temperature, density, and entropy, and the computer essentially blurs them together to calculate fluid pressure.
And both are hard.
Both methods are computationally brutal.
And it's not just the fluid dynamics, right?
Yeah.
Because once the gas does cool down and form stars, those stars start fighting back.
Yes. That is the crucial concept of baryonic feedback. In the late 90s and early 2000s, cosmologists ran these early hydrodynamic simulations, and they ran into a massive problem called the overcooling problem.
Overcooling? What did that look like?
Basically, the gas in the simulations cooled too efficiently. It fell into the center of the dark matter halos and formed stars at a ridiculous rate. The simulated galaxies ended up being way too massive, way too compact, and formed far too many stars compared to what we actually observed through telescopes.
There were just star factories on overdrive.
Exactly. The simulations were completely failing to match reality.
Because they were missing the explosions. They were modeling the stars being born, but they weren't modeling what happens when the massive ones die.
Precisely. They were missing supernovae, and they were missing supermassive black holes. A galaxy is not just a passive collection of stars. It is a highly volatile, finely balanced ecosystem. When a massive star dies in a supernova, it doesn't just disappear quietly. It detonates with unimaginable energy, violently heating the surrounding gas and physically blowing it out of the galaxy in massive galactic winds.
It's like the galaxy is an engine and the supernova is an exploding piston that blows the fuel line apart. If the gas gets blown away, the galaxy is suddenly out of fuel, so it stops making new stars.
Yeah.
Star formation shuts down.
Perfect analogy. And if supernovae weren't enough, you have to model AGN feedback.
AGN.
Active galactic nuclei. At the center of almost every galaxy is a supermassive black hole. As gas falls into the black hole, it forms an accretion disk that gets so incredibly hot it outshines the entire galaxy.
Wow.
It generates colossal jets of high-energy particles that blast out into space, heating up the gas in the dark matter halo and preventing it from ever cooling down to form stars. Injecting that kind of localized, extreme violent energy into a massive, large-scale cosmological simulation requires a level of computational finesse that we have only recently begun to master.
Which brings us to the hardware. Because capturing the sheer explosive chaos of a single galaxy is hard enough. Trying to mathematically calculate the shock wave of a dying star or the jet of a black hole requires solving differential equations over incredibly tiny time steps.
Very tiny.
But doing that simultaneously for tens of thousands of galaxies across a massive chunk of the observable universe. We are talking about true computational leviathans. I mean, my laptop fan sounds like a jet engine taking off just because I have too many browser tabs open.
We've all been there.
I literally cannot fathom the IT infrastructure required to run a virtual universe.
The computational scale is difficult to properly articulate. Modern cosmological projects like the Illustration G project or the EGLE simulation, they are not run on desktop computers. They run on the world's most powerful supercomputing clusters.
Like warehouse-sized things.
Yes. We are talking about machines utilizing tens of thousands, sometimes millions, of CPU and GPU cores operating in perfect tandem. A single large-scale simulation can take months of continuous, uninterrupted operation. Months. And if a single node in the supercomputer fails, the code has to be robust enough to recover from the last saved state without corrupting the entire virtual universe.
And the data output. We aren't talking about a gigabyte file you can put on a thumb drive. The data sets they produce reach petabyte scales.
It's astonishing.
For context, for you listening, 1 petabyte is roughly the equivalent of 250,000 high-definition movies. You would have to sit in front of a television 24 hours a day for over 50 years just to watch that much data.
And that's just to watch it. Scientists have had to invent entirely new database architectures and visualization software just to store and navigate these immense virtual environments. You literally can't load the whole simulation into memory at once. You have to stream it piece by piece just to look at it.
That is insane.
And yet, despite utilizing the most powerful machines ever constructed, there is a profound fundamental limitation we have to face. These simulations, as incredibly detailed as they are, remain coarse-grained approximations.
They're still approximations.
Yeah. Computers, no matter how powerful, cannot mathematically model every single atom or even every single star individually across an entire observable volume of the universe. Consider the dynamic range required. You are trying to simulate a cosmic web that is hundreds of millions of light years across, while simultaneously trying to resolve a supernova shockwave that is a fraction of a light year across.
You just can't do both.
It is computationally impossible to resolve both scales simultaneously.
So if the computer can't see the individual stars or the individual supernovae because they are smaller than the smallest pixels in the simulation, how do they run the feedback? How do they get the supernovae to blow the gas away if the simulation doesn't even know the supernova exists?
They rely on what is arguably the most controversial and essential technique in computational astrophysics, subgrid physics.
Okay, we need to spend some time on subgrid physics because this feels like a massive conceptual leap.
It is.
I like to think of it like trying to predict traffic in a massive city like Tokyo or New York. You don't need a supercomputer to track every single turn signal, or every time a driver hits the brake pedal, or the RPM of every individual engine to know that there's a massive traffic jam forming on the main highway at 5:00 p.m.
Right. You don't need that.
You don't need the micro details. You approximate the local chaos to understand the macro flow.
That is an incredibly apt analogy. Subgrid physics utilizes statistical models to represent those smaller scale processes that occur strictly below the simulation's resolution limit, the grid size.
Okay.
For instance, the simulation might have a spatial resolution of 1,000 light years. It cannot track the fiery mechanics of one specific star going supernova because that star is completely sub-resolution.
It's invisible to the grid.
Yes. However, based on theoretical physics and smaller-scale, high-resolution models, the developers know that a certain amount of gas of a certain density and temperature will produce a specific number of supernovae over a specific period of time.
So instead of simulating the bomb exploding, they just mathematically inject the heat of the explosion into that 1,000 light-year cell.
Exactly. The code essentially says, this cell has met the conditions for star formation. Statistically, X number of supernovae just occurred here. Therefore, I will artificially inject Y amount of thermal energy and Z amount of momentum into the surrounding gas cells.
It just cheats the physics a little bit.
It averages out the unobservable microphysics to faithfully reproduce the macro-scale effects on the galaxy.
I have a real problem with this conceptually. I understand why it's necessary for the computers to not melt down. But if we're using approximations, if we're manually writing code that says, inject this much energy when this happens, Aren't we just baking our own assumptions into the cake?
That's the big question.
How do we know the simulation is actually revealing the underlying truth of the universe, rather than just spitting our own biased theories back at us? It sounds like tuning a guitar until it plays the note you want, and then declaring you've discovered music.
That is the precise epistemological paradox that critics of cosmological simulations frequently raise. Are these predictive scientific tools, or are they highly sophisticated post hoc fitting exercises?
Exactly.
It is a deeply valid critique. If you manually tune the subgrid parameters for supernova feedback just to make sure your simulated galaxies match the exact size of the Milky Way, you haven't necessarily proven how the Milky Way formed, you've just reverse engineered a specific result.
Right. So how do the scientists defend against that? How do they prove this is actual science and not just cosmic video game design?
By demanding predictive power across multiple distinct observational metrics, a robust simulation like Illustris TNG is calibrated. The team tunes the subgrid parameters so that the simulation correctly matches a very specific baseline observation, usually the stellar mass function.
What's the stellar mass function?
Which is simply the abundance of galaxies of different masses in the present-day universe. They adjust the feedback dials until the simulation produces the right ratio of large galaxies to small galaxies.
Okay, so they calibrate to one specific metric. They tune the guitar to one string.
Yes, but here's the critical test. Once those parameters are locked in to match the mass function, they do not touch the dials again. They let the simulation run.
Hands off the keyboard.
Hands off.
Okay.
And then they ask, does this simulation, which was only tuned to match galaxy masses, naturally reproduce other completely unrelated phenomena?
Like what?
Does it produce the correct clustering of galaxies across the cosmic web? Does it naturally produce the observed division between blue star-forming spiral galaxies and red dead elliptical galaxies? Does it correctly map the distribution of heavy metals like oxygen and iron in the intergalactic medium? Does it reproduce the mysterious magnetic field topologies we see in galaxy clusters?
Astonishingly.
Yes.
Wow.
When the physics are implemented correctly, these simulations reproduce a staggering array of observational data that they were never explicitly tuned to match. The math checks out.
That's incredible.
They are generating mock telescope observations that perfectly mimic the large-scale gravitational lensing patterns we see in the real sky. In many instances, if you take a simulated galaxy from the high-resolution runs and apply synthetic telescope noise to it, it is virtually indistinguishable from a real image taken by the Hubble Space Telescope.
You can't tell the difference.
Even trained astronomers struggle to tell which is the mathematical abstraction and which is the real universe.
That convergence between simulation and observation is wild. Because traditionally, the scientific method is all about direct experimentation. You want to know what a chemical does? You put it in a beaker, you add a reagent, you heat it up, you measure the reaction.
Right.
But cosmology has a fundamental constraint. We only have one universe.
Yeah.
We are stuck inside it.
Yeah.
We can't put the Big Bang in a petri dish.
Yeah.
And we can't rewind the actual universe to see what would happen if things were different.
Exactly. Astrophysics is traditionally an observational science, not an experimental one. We can only look at the history the universe decided to give us.
Until now.
Right. These highly accurate predictive simulations completely change that paradigm. They cease to be just sophisticated visual aids. They function as true, rigorous computational experiments. They become active laboratories where human researchers can test hypothetical physical laws and compare the outcomes against the reality we observe in the night sky.
We are essentially allowing human beings to play God with the laws of physics inside a machine. We get to tweak the dials of reality. What happens if we run a simulation where we alter the properties of dark matter just a tiny bit?
That is precisely how we test competing theories of physics. For example, let's take dark matter. The standard model assumes cold dark matter, meaning the particles move very slowly compared to the speed of light.
Cold means slow.
Yes. This allows them to clump together easily, creating small structures that merge into larger ones, a bottom-up formation. But what if dark matter is warm? What if the particles are lighter and move much faster?
If they're moving faster, they wouldn't clump together as easily.
Right.
They would buzz out of the small gravitational wells.
Precisely. So researchers run the exact same massive simulation, but they change the fundamental velocity properties of the dark matter particles to match a warm dark matter theory. They hit play, let 13 billion years pass in the computer, and then look at the results.
And what do they find?
In a warm dark matter universe, the massive filaments and large galaxies still form, but the thousands of tiny dwarf galaxies that usually swarm around massive galaxies like our Milky Way are completely wiped out. The fast-moving dark matter simply smoothed out the small-scale structure.
So then you take that virtual output, you look at the real Milky Way, and you say, well, the real Milky Way does have dozens of dwarf galaxies orbiting it.
Exactly. Therefore, the warm dark matter model must be wrong, or at least highly constrained. If a tweaked parameter causes the simulated universe to fundamentally break down if galaxies fail to form, or the cosmic web looks entirely wrong compared to massive sky surveys like the Sloan Digital Sky Survey, then that specific theoretical model of particle physics is discarded.
It just doesn't survive the test.
It is a ruthless computational process of elimination.
And one of the biggest, most terrifying dials they're trying to figure out how to tune is dark energy. We mentioned it earlier, but it is such a profound mystery.
A huge one.
For most of human history, we assumed the expansion of the universe, which started with the Big Bang, would eventually be slowed down by the collective gravitational pull of all the matter inside it.
Like tossing a ball in the air.
Yeah, exactly. It has to come back down. But in the late 1990s, observations of distant supernovae reveal the exact opposite. The expansion of the universe is actually accelerating. Space is pushing itself apart faster and faster.
It was a Nobel Prize-winning discovery that completely upended physics. In the standard cosmological model known as lambda CDM, this dark energy is represented by lambda, the cosmological constant.
The cosmological constant.
It acts as an intrinsic, pervasive, repulsive energy of empty space itself. As space expands, there's more empty space, which means there's more repulsive energy, driving even faster expansion.
What is it really?
The true physical nature of dark energy remains completely unexplained. Is it the vacuum energy of quantum fields? Is it a dynamic, changing scalar field, often called quintessence? Or do we fundamentally misunderstand how gravity operates on colossal scales?
So we put these different theories of dark energy into the supercomputer. What do the simulations tell us if we play with that specific dial? What happens if dark energy doesn't remain constant, but actually gets stronger over time?
If you program a simulation where the dark energy equation of state the dial dictating its strength increases over time, you enter a scenario known as the Big Rip.
The Big Rip. That sounds bad.
It is. The simulation shows the repulsive force of space eventually overpowering everything. First, it pushes the galaxy clusters apart. Then, the repulsive force grows so strong it overwhelms the gravity holding individual galaxies together, stripping stars away from the core.
Oh, wow.
Eventually, it overwhelms the gravity of planetary systems, tearing planets from their stars. In the final moments of the simulation, the expansion outpaces the electromagnetic and strong nuclear forces, and the very atoms themselves are ripped apart.
Okay, that is deeply bleak.
Very bleak.
But what if we just stick to the standard model? What if dark energy is just a constant, unchanging force, exactly as lambda CDM suggests? The simulation must show us where our actual real universe is heading.
It does, and the implications are haunting in a quieter way.
How so?
If dark energy remains constant, the accelerating expansion continues unchecked. The simulations reveal that the cosmic web, as we see it today, is a temporary structure. Over tens of billions of years, the gravitational bonds holding the larger web together will fail. The voids will expand relentlessly.
Everything just drifts apart.
Yes. Galaxies that are not already bound together by local gravity will be pushed away from each other at speeds exceeding the speed of light.
Wait, I thought nothing could move faster than the speed of light.
Nothing can travel through space faster than the speed of light. But space itself has no such speed limit. It can expand at any rate. The simulations show that eventually, distant galaxies will be pushed beyond our observable horizon. The light they emit will never be able to traverse the rapidly expanding space between us.
That means that future civilizations, if biological or synthetic life manages to survive billions of years from now, are going to wake up in an incredibly lonely universe.
Very lonely.
They might inhabit isolated galactic islands, just the merged remnants of their local group of galaxies. They would look out through their ultra-advanced telescopes, expecting to see a vast cosmos, and they would see absolutely nothing.
A completely black, empty sky.
All the evidence of the Big Bang, the cosmic web, the billions of other galaxies that we're privileged enough to observe and simulate today will have been permanently erased from their observable horizon. They might falsely conclude that their single solitary galaxy is the entire universe.
It is a profound existential insight derived directly from the numerical outputs of a supercomputer. We are living in a privileged observational epoch. We happen to exist at a time when the universe is old enough to have formed complex galaxies and conscious observers, but young enough that dark energy hasn't yet erased the evidence of our origins.
And this brings up another existential revelation from these computational experiments, the sheer terrifying fragility of our reality.
The fine-tuning problem. It is inescapable when you work with these simulations. They prove mathematically that our universe is incredibly, almost absurdly sensitive to its initial conditions.
The dials are very touchy.
Exactly. If you alter the parameters just a microscopic amount, if you change the initial expansion rate of the Big Bang, if you shift the density of dark matter by a tiny fraction, or if you make those primordial quantum fluctuations in the CMB just slightly smaller or larger, you produce dramatically different sterile universes.
I read about one where they just slightly lowered the initial density fluctuations. And what happened? The dark matter never gathered enough mass to overcome the expansion of space. Right.
Galaxies simply failed to form entirely. The universe remained a diffuse dark fog of hydrogen gas, forever expanding, forever cooling, no stars, no carbon, no biology.
Or conversely, if you make gravity just slightly stronger, or the expansion rate slightly slower, the entire universe collapses back in on itself in a big crunch before stars even have time to ignite.
Wow.
The window of parameters that allows for the formation of stable cosmic web structures, long-lived stars, and the complex chemistry necessary for life is infinitesimally narrow.
So how do scientists grapple with this? If tweaking the code just a tiny fraction ruins the whole simulation and prevents planets and humans from forming, does this suggest our existence hangs by a mere mathematical thread? Do we just accept that we got incredibly, improbably lucky in a cosmic lottery?
It's a huge debate.
Or does this fine-tuning point to something else? Does it imply there's a deeper, unifying physical law that naturally locks those dials into place and we simply haven't discovered the math yet? That represents the very bleeding edge of modern theoretical physics. The simulations don't answer the why, they only illuminate the what. This immense fine-tuning highlights how beautifully balanced cosmic evolution appears to be. For some physicists, it strongly implies the existence of a multiverse.
The idea being, if you run infinite simulations with random parameters, most of them will be dead, sterile fogs. But simply by statistical inevitability, one of them will roll the exact right numbers to create stars and life.
Right.
And because we are alive, we must necessarily be in the one that worked, the anthropic principle.
Exactly. But for others, invoking a multiverse is an intellectually unsatisfying cop-out. They believe that a future, deeper fundamental theory, perhaps a complete theory of quantum gravity, like string theory or loop quantum gravity, will eventually reveal that these parameters are not random dials that can be freely tweaked.
They have to be what they are.
A deeper theory might dictate mathematically that the universe must have exactly the dark matter density and dark energy values that we observe. But that remains completely unresolved. What is undeniably proven by these computational experiments is precisely how delicate and improbable the long chain of physical events was that allowed you and me to exist and have this conversation.
To push these boundaries further, to try and solve these ultimate mysteries, we need to run more experiments. We need to test thousands of different dial tweaking scenarios, run higher resolutions, and resolve both the massive cosmic web and the individual supernovae simultaneously.
We need more power.
Right. But human minds, and even our traditional algorithms, are hitting a limit. So we are now enlisting the help of artificial minds. AI and machine learning are fundamentally rewriting how we simulate the universe.
The integration of artificial intelligence into cosmological simulation represents a massive, necessary paradigm shift. Remember the petabyte-scale datasets we discussed?
The 50 years of movies.
Yes. The sheer volume of output is overwhelming. Human beings, even teams of thousands of postdocs, simply cannot comb through that much information efficiently. Machine learning systems, particularly convolutional neural networks, are incredibly adept at analyzing these massive, multidimensional data sets. They can identify deeply hidden, nonlinear patterns in the cosmic web that human intuition would completely miss.
But AI isn't just acting as a highly efficient data janitor.
Right.
It's not just sweeping up the data after the simulation is done. AI is actively helping to build the virtual universes faster.
Yes, through the development of AI surrogate models, or emulators, we talked about how computationally expensive subgrid physics and fluid dynamics are. A high-resolution simulation calculating every thermal shock wave can take months.
Right.
But what if we don't have months? What if we want to test 10,000 different dark energy models? We can't wait 10,000 months. So researchers train an AI on a small, insanely detailed high-resolution simulation. The neural network learns the deeply complex physical mapping.
It finds the shortcuts.
Exactly. It learns, when the dark matter density looks exactly like this, the resulting gas temperature and star formation rate will look exactly like that.
It bypasses the traditional math. Instead of calculating the fluid dynamics step by step using the Euler equations, the AI just looks at the initial state and immediately predicts the final state based on the patterns it learned.
Exactly. It emulates the physics. Once the AI is trained, they can deploy it across a massive scale, low-resolution dark matter simulation. The AI instantly paints the highly complex, realistic baryonic gas and stars onto the dark matter skeleton in a fraction of the time.
That is brilliant.
It dramatically saves millions of hours of supercomputing time while rigidly preserving an astonishing degree of scientific accuracy. This allows us to run vast parameter sweeps that were literally impossible 5 years ago.
And we're going to need that speed because the data pipeline from real-world astronomy is about to explode and the simulations are going to have to keep up. We are looking at future computing horizons like exascale architectures, machines like the Frontier supercomputer, capable of performing over a quintillion calculations per second.
A billion operations a second.
And we need that power because the telescopes are getting too good.
The dialogue between observation and computation is entering an era of unprecedented tension and precision. The James Webb Space Telescope is currently peering further back in time than human eyes ever have, looking at the very dawn of galaxy formation. And it is finding massive, fully formed galaxies existing much earlier in the universe than our current simulations predicted.
It's breaking the models.
It is actively stressing our subgrid models of star formation.
The models said those early galaxies shouldn't have had enough time to get that big. JWST is looking at the sky and saying, your code is wrong.
Precisely. And that is exactly how the science advances. JWST provides the tension, and the computational astrophysicists must return to the supercomputers, refine their models of dark matter or early baryonic feedback, perhaps introduce new mechanics like bursty star formation or primordial black holes, and run the simulations again until the virtual universe matches the new reality.
It's a constant feedback loop.
Furthermore, we have the upcoming Vera C. Rubin Observatory, which will map the entire southern sky every few nights, generating an absolute tsunami of data regarding dark matter lensing and cosmic expansion.
The Vera Rubin is going to catalog billions of galaxies. To make sense of that, we need simulated universes that contain billions of simulated galaxies to compare them against.
Exactly. As JWST and the Vera Rubin Observatory gather vastly more precise data, our simulations will become increasingly, relentlessly constrained by reality. We will be forced to simulate magnetic fields, general relativistic effects, and complex chemical evolution with a resolution we previously thought impossible.
That is just going to get more and more detailed.
We are approaching an era where entire observable volume universes may be mathematically modeled at resolutions currently reserved for a single isolated galaxy.
I want to take a step back from the terabytes and the algorithms for a moment and just look at the existential reality of what we have discussed today. Because there is something deeply, overwhelmingly poetic about this entire endeavor.
There really is.
We are a biological species. We evolved to hunt, gather, and survive on a rocky planet orbiting a very average yellow star. We have possessed electricity for less than a couple of centuries. We have been looking through telescopes for a blink of a cosmic eye.
Just a blink.
And yet somehow, the physical matter inside our skulls has developed the mathematical capacity to reverse engineer and reconstruct the entire 14 billion year history of the universe that created us.
It is the most profound recursion imaginable in the natural world. Let us trace the physical path we've outlined today. The universe begins as incomprehensibly tiny random quantum fluctuations in a primordial soup. Through entirely deterministic, unthinking physical laws, gravity, thermodynamics, fluid dynamics operating silently over billions of years in the dark, those fluctuations evolve. They collapse into a dark matter web. They ignite into stars. Those stars forge heavy elements like carbon and iron in their cores and explode them out into the void.
Spreading the seeds.
That complex chemistry eventually coalesces into planets and ultimately generates conscious biological observers.
Us. And then Those conscious observers extract silicon from the Earth, construct sophisticated mechanical brains out of it, and program those supercomputers to build internal mathematical models capable of perfectly reproducing the universe's own history, right back to the quantum fluctuations.
It is exactly as if the universe spent 14 billion years growing a biological brain, just so that biological brain could build a mechanical brain, all to dream about how the universe was born in the first place.
That is just beautiful.
Through these computational laboratories, we are the cosmos performing self-reflection. We are the universe trying to understand itself.
And I think the visual beauty of these simulations completely reinforces this awe. When you look at the outputs of projects like Illustris or the Millennium simulation, the vast twisting filaments of dark matter stretching across the blackness of space look remarkably, undeniably like luminous neural networks.
The resemblance is uncanny.
The largest macrostructures of the universe visually echo the microstructures of the human brain that is currently simulating them. The universe appears simultaneously, intensely, coldly mathematical, and deeply, beautifully organic.
It completely changes how we view the very nature of reality itself. These simulations demonstrate unequivocally that staggering, awe-inspiring complexity naturally emerges from ultimate simplicity.
Right, you don't need a complicated start.
No, you start with a few simple rules, a few basic fundamental forces, and a slight imbalance in density. You give it 14 billion years of processing time, and you get everything. The cosmic web, the galaxies, the planets, and the minds capable of understanding the math.
But despite all of this computing power, despite the AI and the exascale machines, we have to remain humble. Because these simulations also explicitly define the boundaries of human ignorance.
Oh, absolutely.
The universe remains fundamentally mysterious. We can model dark matter flawlessly, but we have never directly detected a dark matter particle in a lab. We can code dark energy into the simulation, but it remains completely unexplained in fundamental physics. The crucial unification of quantum mechanics and gravity, the very thing required to understand the literal instant of the Big Bang, remains unresolved.
It's the holy grail of physics.
Every single virtual universe we boot up inside a supercomputer is built upon a foundation that contains a vast ocean of known unknowns.
That humility is essential. A simulation is only as good as the physics programmed into it. But the progress is undeniable. We are no longer just guessing at how the invisible shapes the visible. We are testing it.
We are proving it.
Yes, we are proving that our reality possesses a deep underlying order. An order capable of being represented mathematically across scales of time and space that utterly defy daily human intuition.
Let's bring this grand journey full circle. Think about the sheer mind-bending scale of what we've explored today. We started with microscopic, 1 in 100,000 quantum ripples preserved in the ancient light of the CMB.
The very beginning.
We watched those ripples get magnified by gravity, pulled into an invisible, collisionless dark matter skeleton. We saw how chaotic, hot, turbulent, ordinary gas falls into those structures, battles against the explosive feedback of supernovae and supermassive black holes to finally ignite the galaxies we know and love.
It's a chaotic ballet.
It really is. We talked about how computational astrophysicists are mathematically rebuilding all of this, using petabytes of data, running complex fluid dynamics on millions of processing cores, and tweaking the physical dials of reality to see what happens. All while artificial intelligence helps us untangle the unimaginable complexity of the results.
It is a testament to the fact that profound intelligence can arise within a universe vast enough to contain both the crushing gravity of dark matter halos and the fragile biological minds capable of deciphering their equations.
Which brings us to one final, deeply provocative thought. Something for you, listening right now, to ponder long after you stop the playback today. We have talked extensively about how our supercomputers are already generating entire observable universes. They're utilizing complex subgrid physics and AI emulators to produce simulated galaxies that are virtually indistinguishable from real telescope images. We've established that incredible organic complexity inevitably arises from simple mathematical rules executing over vast stretches of time.
Right.
So if we can simulate a universe this accurately today, imagine what we will be able to simulate in 100 years, or 1,000. What happens when a simulation running inside one of our descendants' machines becomes complex enough and operates at a high enough quantum resolution to naturally develop its own simulated conscious observers?
Observers who evolve on a simulated rocky planet.
Yes, who look up at their simulated stars, build their own simulated computers, and try to mathematically model their own origins. And if that recursion is mathematically possible, if simulated universes can spawn their own simulated minds, How can we be absolutely, fundamentally certain that we aren't already living inside one of those computational experiments right now?